Hello, welcome to our last set of notes for Unit 3, Probability. This last set, we're going to talk about counting, which sounds silly to talk about when we talk about probability, but we're talking about counting really large values. So a lot of times when we're doing probabilities, the number of choices, the number of arrangements or groups that you can pick from can get really large. So you need to have special techniques to count these so we don't have to actually sit there and count them. They're going to be millions, billions, even bigger. So far, we've been getting by with the multiplication principle, where we just look at the number of choices for each option, multiply those, and that's great. But for some of these more advanced situations, there might be faster, easier techniques, and that's what we want to get into. So the first type we're going to talk about is arrangement with repetition. So suppose you want to make a license plate, you're only using 5 numerical digits, so 0 through 9. Since it deals with 5 choices from a group of 10 digits, so we're looking at 5 choices, and we have 10 digits to choose from, 0 through 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 choices. And we're at allowed repetition. When you make a license plate, you can go again. We call this an arrangement with repetition, and it's calculated as follows. So because you're making R selections from N choices, the number of different arrangements. So here arrangements means, all the different orders matter. So A, B, C is different than C, D, A. Is n times n times n times n r times, or n to the r power. Because if you think about the multiplication principle, every time you choose, you have 10 digits to choose from, you have n choices to choose from, that's what n is. So like up here, the example here, we would have 10 is our number of choices, because you have 10 digits, and 5 would be the power. So this one would just be 10 with 5 zeros, 3, 4, 5. So 100,000 choices is 5, length 5-digit license plate. So which makes sense, because if you think about 5 digits, you have everything from 5 zeros all the way up to 5 nines, and that's 10,000 numbers. 0 through 99,999. So anytime you're allowed repetition, you can just multiply the same value over and over again, and the number of times, the power, that's just how many choices you're making. Since we only had 5 places in the license plate, that was what? It's the 5th power. If it had been an 8-digit license plate, we would have 10 to the 8. How many 7-number license plates can be made if we again allow repetition? So we go down and we do, 7 license plates, 7-digit license plates. Now we're just doing still 10 numbers, so we have 10 choices, and we have 7 for the power, that's going to be our R. And because we're using, numbers still, 0 through 9, that's why it's 10. And so we'd have 10, have 7 zeros. 3, 4, 5, 6, 7. So we'd have 10 million choices, because we have 10 to the 7th. So that would be that. How many possible license plates could we make using 5 capital letters? So maybe instead of using digits, now let's use capital letters. Now, because we're only using capital letters, that means we can only use one feature letter of the alphabet once. So we, of course, have 26 letters to choose from. I'm not worried about lowercase versus capital. We're just doing 26 capital letters. And now we're choosing 5 of those. 5, chosen. We're allowing repetition again, so we can use the same letter over and over again. But we only have 5 choices we're making. So this time 26 would be our N, and 5 would be our R. The biggest thing people messed up with this formula is using it, 1, when there's no repetition allowed. This only works if you're allowed to repeat. And 2, switching N and R. So just make sure you keep track of which one's which. Remember, N is how many you can choose from, and R is how many you're actually choosing. So this one would be 26 to the 5th. Now, I'm not going to do that in my head. That's why it's nice to have a calculator. So I would do 26 and type my power, do 5, and we get quite a big number, right? So what is that? 11 million, I think? Maybe a little more than that. So yeah, this one we get 1, 8, 8, 1, 3, 7, 6. So almost 12 million, just from using 5 capital letters. If we instead combine these 7 numbers and 5 letters, so instead of just doing, the 7 numbers or the 5 letters. Let's do all put together. So we're going to have a license plate that has the 7 numbers and then the 5 letters in that order. How many possible combinations could we make? Well, since we have 10 million choices for those first 7 numbers and almost 12 million for the next ones, remember that if we know the number of choices for each part, we can use that multiplication principle, and we can just multiply those together to get the answer. So I'm going to, just because I want to rewrite these numbers because they're so big, I'm just going to do 10 to the 7th times 26 to the 5th. So multiplying these two numbers together. When you multiply by 10 million, you just add a bunch of zeros. So I'm going to have the 11, 8, 8, 1, 3, 7, 6, and then we have 1, 2, 3, 4, 5, 6, 7 zeros. So 1, 2, 3, 4, 5, 6, 7 zeros. Now this, their number, what was that? Thousands, millions, billions. So 118 trillion options. So just using 12 symbols, 7 numbers and 5 letters, you already have 118 trillion options. And you can see what I was talking about. These numbers, quantities can get big fast. Like if I had let us use 12 numbers or letters, not just 7 numbers and then 5 letters, we'd have had even more options. We had way more options. So this is why we can make enough license plate for everybody to have their own unique license plate. There's so many options just by having 10, 12 digits. This way in Wyoming, we're in South Dakota, close to Wyoming, but Wyoming has pretty short license plates because they don't need very many because there's not a very big population there. All right, next, permutations. So we still want to worry about order, but what about if you're trying to pick 4 swimmers for a relay? Now in this you can't repeat because one person can't swim more than 1 lap. If you tired out, it's not part of the rules. So each person can only do 1 lap. So the order is important because you have to think about like the different ways you can arrange it. Who swims first, who swims last. It's going to change how well they do. But we can only use this once each. We call these permutations when the order matters and there's no repetition. And that's kind of the big difference between the first one. So the first page we will always use for when there was repetition, but for permutations we're going to say, okay, order matters, but the other big thing is there's no repetition. Okay, so here's a chart where they actually showed how to figure this out. So you look, okay, first leg, there's 4 people you can choose from. After you choose A for the first leg, well then you can only choose B, C, or D. If you chose B, then you'll only be able to choose C or D for the third leg. If you chose C for the third leg, then D is forced because that's the only one left. And so on and so forth. Like if you pick B and then C, then you have A or D. If you pick A, you'd have D left. And so each one of these is a different set you can pick. So you end up with all these different orders. So each one, 1, 2, 3, 4, 5, 6, by 4, you end up with 24 orders. So just with 4 people on the swim meet, there's actually 24 different ways you could arrange them. The different orders you could put them in. And that's a lot, just for 4 people. Only 4 places for 4 people. The number of orders grows really quickly if you have more choices or more people to choose from. So we're going to keep the number of orders using this formula. We're going to take the number and then multiply it by every smaller number down to 1. So we're just multiplying by the whole number. So like in this case up here, we would have had 4 times 3 times 2 times 1. We start with 4 people, and then we have 3 choices, 2 choices, 1. So you can see we had 4 in the first row, and then 3 in the second row, and then 2 in the next row, and then 1 in the last row. You multiply 4 times 3, you get 12, times 2 gives you 24, times 1 stays 24, and that's how we got the 24 orders. This, we're going to talk more about, this is a symbol used for this, it's called n factorial. We'll talk more about it on the next page, but that's the way we multiply these. So that's the part I need to know. This is when you're choosing all the elements, but there's no repetition. So we're looking at the number of arrangements, the number of orders, but there's no repetition. So you can't use the same thing twice. So say you want to do, you have a team of 6 students running a race. How many ways you could order for a 6-person race? You want to think about all the different ways you could arrange them. So in this case, because there's 6 people, we just do this 6 factorial. We do 6 times 5 times 4 times 3 times 2 times 1. Multiply that out. You don't have to do it in your head. That's kind of nice. You don't have a calculator. You can just sit there and type it in. 5 times 4 times 3, and multiply it out. Get your answer. So this is 720. You see how much bigger it is. We only went up to 6, and now we went from 24 all the way up to 720 just by going up to 6. If we go even, 8, 9, 10, it's going to get bigger and bigger and bigger pretty quickly. Okay, that's simple factorial. It's important. You'll see it a lot in the rest of the section, so let's talk a little bit more about it. So products where you have a countdown like this, you start with a number and you just go all the numbers small until you get to 1. Very common probability. We use them all the time when we're counting big sets of numbers. Basically, anytime you're not doing repetition, you have to worry about each choice. You have less options, basically. That's where this comes from. It's been called factorials. The symbol exclamation point is used to indicate a factorial. So for any positive number, integer, n, multiplied by all the preceding positive integers, we call the result n factorial. So 1 factorial will just be 1, because it's 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, 4 factorial is 4 times 3 times 2 times 1, 5 factorial is 5 times 4 times 3 times 2 times 1. And you can see they get big fast, right? 120, we're only 5 in and we're already at 120. It grows really quickly. In fact, your calculator can't handle anything like 70 or bigger. So if I tried to type here, type in here 70 times 69 times 68, it wouldn't work. In fact, some calculators actually have a factorial button. My TA30 doesn't, so I'm not going to use that much, but if I wanted to show you, I'll do 70 factorial on this calculator. I don't know if I remember where it is, probability. There it is, number 4. Okay, 70 factorial, you type it in and it says overflow error. An overflow error in a calculator means that the data storage place where it has memory to keep the value is full. Basically, the number got so big, the calculator couldn't fit it in its storage, in its memory. It got too large for it to work with. And so it just had to stop. It's like, nope, I can't do this anymore, and you have to quit. So you can't do anything bigger than 70 factorial. Thankfully, we won't usually see that. It's something I have to worry about. But yeah, that's actually a thing that these ones, they get really big really fast. Also, by definition, 0 factorial is 1. There's a few times where we'll see 0 factorial pop up, and if it does, just remember that it is worth 1. It's not 0. 0 factorial is 1. It's kind of weird that 0 factorial, 1 factorial are the same amount, but just in the sense of probability and stuff, math has just decided that's kind of the easy way to deal with 0 factorial. Now, we will see some factorials pop up in fractions, and so you'll see some of this in the homework, and you'll see it in the later parts of the section. So I just wanted to go over how we deal with these. So we see a fraction like 5 factorial over 3 factorial. Of course, that means 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. That's what it means. But what you'll notice is that we have the 3, the 2, and the 1 on both the top and the bottom. So they really can end up canceling, because we have multiplication written out like multiplication like this. You can cancel any common parts to the top and bottom. So this really just becomes 5 times 4, or 20 for an answer. You'll notice you can kind of shortcut from the original part to getting to this 5 times 4. And if you notice that when you have 5 over 3, everything 3 or smaller is going to cancel, because with factorials, they're doing the same countdown. Here they're just starting at for different first numbers. One starting at 5, one starting at 3. So anything that's above 5, that's going to be what we actually multiply. So here we didn't have 5 times 4, we had to multiply the 5 times 4. Everything smaller we didn't worry about. So then I get to a problem like this one, I don't have to list out 15 factorial, 13 factorial. I know this is going to be 15 times 14. Because everything 13 and smaller cancels. Again, if I think about this as 15 times 14 times 13 factorial, because after the 13, I'm just get all the numbers smaller over 13 factorial. Think about how the 13 factorial is going to have the same thing on top and bottom, but we're going to be left with is 15, 14 on the top. And that's where we get our answer that way. So 15 times 14 is, so 15 times 14, I get 210, so 210 will be the answer. So it's a little shortcut way of dealing with this. Whenever you have a fraction like this, we'll typically have the bigger value on top. Well, that's pretty common for these. We'll look at it and say, okay, whatever's on the bottom, cancel that and smaller, just leave what's bigger. So it makes a number like this one. This one's so much easier to do this way than doing the calculator or something. You just say, oh yeah, 100 factorial is going to cancel with 100. The only thing that's left here is 101. Yeah, that's the answer. Because if I had 101 times 100 factorial, that's the same thing as 101 factorial, because you have 101 times 100 times 99 times 99. You got all those things for 100 factorial. Again, the 100 factorials are canceling. You're just left with 101. The one other thing you will see with these is you'll see some where they have multiplication on the bottom as well as the fraction. So what I would do with these is I would still cancel, but I would cancel the bigger of the two. So I'd take this and I'd get 6 times 5, and I'd cancel the 4 factorial. But then the 2 factorial is still there because that's not part of this 4 factorial. So I'd still have a 2 factorial on the bottom. So this would end up being 6 times 5 over 2 times 1, which is not too big a deal here. This would end up with 30 over 2 or 15. But anytime you have like multiples on the bottom, just cancel the biggest one. So I'm canceling, I'm thinking about how 6 times 5 times 4 factorial would be the top. I'm canceling the 4 factorial with this 4 factorial. I'm just leaving the 6 and the 5, the 2 factorial. That's about the hardest we'll get with factorials. Again, that's what they are. They're just all numbers multiplied down. So a lot of times if you have a fraction, I have to do some canceling. Okay, now why we see this fraction is because we get to the situation where instead of selecting everything, if you noticed, I guess I should mention a couple pages back, we did the permutation formula, we did n factorial. When we did this, we were choosing all the elements. So everything was being chosen. We weren't leaving anything behind. Now in real life, a lot of times you pick out of a group. So if you don't pick everything, then you actually end up with a lot more choices, because you have more stuff left over and you have more different, possible combinations. And so it can really change your, number of outcomes. So suppose you had 4 swimmers on your team. Instead of 4 swimmers on the team, you actually have 10 members on your team. If you're trying to pick a team of 4 members for a relay, now you got 10 people to choose out of. So you don't have to pick the same 4 people all the time. You could actually pick, a different set of 4 each time. Or you could set, grab some from this team, from that group, mix it up all the time. So now you have lots of different ways to do it. So how do we figure this one out? Well, we use a permutation formula where we're choosing our elements, R is the number of swimmers we're choosing for this relay, so it'd be like R4, out of a set of n elements. And that'd be like the total number we can choose from. Note that n is always bigger than R. Because n is what you're choosing out of. It's the whole group, all 10 people on the swimming team, that'll be n. And R is how many you're choosing. We're only choosing 4 swimmers on the team. I guess I'm figuring 4, 2, 4, I should put R there. 4 members for my team. But so n is always bigger than R. And in the formula, what you do is you do n factorial on the top. On the bottom, you subtract n minus R. This you should always get a positive number because n should be bigger. Subtract, and you get some positive number factorial. This will be smaller than n. That's why we saw most of our fraction will have a bigger number on top, because when you're doing permutations like this, I use the formula NPR. This is just saying the number of things we choose from and how many we're choosing is n factorial over n minus R factorial. Make sure you do the subtraction first, because it's inside the parentheses, and then you'll have a factorial over factorial, and then simplify. So let's do it. Here we're going to choose, suppose you're trying to pick a password for a website that does not use the same character twice. You can make a password with 4 characters. So I got 4 capital letters or numbers only. So first off, notice I have 26 capital letters I can choose from. I have 10 numbers, 0 through 9. I always get people to think it's 9. That'd be if you were doing like 1, 2, 3, 4, 5, 6, 7, 8, 9. You can also include 0. That's why there's 10. So I actually have 36 possible options. Be careful here. We're not doing multiplication principle or anything. We're just saying how many different choices you have. Well, you have 10 possible capital letters, 26 capital letters and 10 numbers. You can choose any one of those 36, for your choice for your password. This is only capital letters for this password. It's not going to distinguish between like capital and lowercase. So you just use one set of letters and the 10 numbers to get our password. So we're choosing out of the 36. We're doing a permutation where we choose only 4 of those. This would be a 36p4, because 36 would be our n, and 4 would be our r. This is how many we're choosing from. This is how many we actually get to choose. And so we do 36 factorial over 36 minus 4 factorial. So again, the bigger number goes on top, and you subtract, and it should be small on the bottom. So I get 36 factorial over 32 factorial. What you'll see is, again, 32 of these are going to cancel. We just keep the top ones above 32. So we're going to have 36, 35, 34, and 33. Those are the only 4 we need, because everything 32 or smaller is going to cancel. We have 4 spots. So I just multiply those out. To get my answer, I multiply 36 times 35 times 34 times 33. Multiply it out. And our answers, we have 1, 4, 1, 3, 7, 20, so about 1.4 million possible arrangements. This is the number of different ways. You can pick 4 letters and numbers to make a 4-character password. Here, notice that it is kind of weird one. We're not allowed to repeat. So, not allow you to use the same character twice. You know, in real life, passwords would be bigger because you actually can use repetition. But in this example, I have to say no repetition because we only use this permutation formula when there's no repetition. So that's something important to really point out, as this is only for no repetition. If you're doing repetition, you go back to the first formula we saw, and to the R formula. This is the pretty simple, straightforward formula. If you're allowed to repeat, you can use this because you can just do the same thing over and over again, multiplying n over and over and over again. So that's what we do if there's repetition. But since there's no repetition, we said you can't repeat. So it's a weird password where you can't use the same number twice or letter twice. Then you'd have less options. You'd have this number of options, and it's that permutation formula. Again, this is for choosing R elements out of n elements with no repetition. So permutations, no repetition. And also notice that the order definitely matters. When you're doing this, order matters because you're looking for the number of different arrangements. So far, everything we've done in this section, order has mattered. We'll get to the last part, and I'll show you what happens if you don't worry about the order. Maybe just try to pick a group and don't worry about the order. But let's do one more example of permutation. Again, to know its permutation, we look for the fact does order matter, and we look for is there repetition allowed. So say a teacher is trying to make a seating chart. If she has 20 students in her class, how many ways could she pick 5 students to sit in the first row? So out of 20 students, she's picking 5 of them. N is going to be the bigger number. It's going to be the total she's choosing from. R is going to be the smaller number. It's how many she's actually choosing. Notice that there is no repetition because you can't pick the same student to sit in 2 different desks. You know, that doesn't work. They sit in this desk or they sit in that desk. They can't sit in both. So there's just one desk option. So order matters, no repetition. And trust me, as a former middle school teacher, the order you choose for your students to sit definitely matters. You put Bobby next to Billy, and all of a sudden you're having tons of trouble. You know, you have to think about the way you arrange them. So there's a situation where order definitely matters. So no repetition, order matters. On the test, I'll make sure it's really clear whether order matters or doesn't. So you'll know, if order matters, then doing a permutation type situation. So this is going to be 20. We're doing permutation 5. So 20p5 because we say out of the 20, we're picking 5. Order matters, no repetition. Okay, no repetition for this. So we do the 20 factorial on top. On the bottom, we do 20 minus 5. And then do our factorial. So it's always the bigger number minus the smaller number on the bottom. So we get 20 factorial over 15 factorial. 20 minus 5 gives 15. And so we're just going to multiply numbers bigger than 15. So 20 times 19 times 18 times 17 60. And that'll give us our answer. So we just have to multiply those, and we'll find out how many different ways you can arrange 5 students out of the group of 20. So we'll multiply 20 times 19 times 18 times 17 times 16. So multiplying those 5 numbers, and we get 1860480. So we've got 1.8 million choices since we're choosing 5 people out of the 20 in our group. So permutations, there's no repetition allowed for permutations, and the order matters. Notice the big difference between this page where we do this permutation formula and the previous page is the previous page we were, this one, we were choosing all the elements. So that's why we just did all the way down to 1 every time for this, because we chose all the elements, we didn't stop. Here, basically what happens is the bottom number just tells you how many to count if we stop. So we go 1, 2, 3, 4, because we do 36 minus 4, you end up with 32, you end up with only using the top 4. So this is always going to happen. The R number 5 is going to tell you how many to count, so I end up with 1, 2, 3, 5. So if I'd chosen all 20, I would have done 20 all the way down to 1, but I chose only 5 of them for this password. So that's the difference here between the m factorial formula where you're choosing all the elements. All right, the last tip I want to show you is combinations. Big difference between combinations and permutations is now order is not important. We don't care about the number of orders, we care about the number of groups. Suppose your coach needs to pick 4 members for your swim team to compete in a 50-meter freestyle. Since the swimmers are competing and they're not swimming in a relay, the order he chooses doesn't matter. He's just saying, hey, I'm going to pick 4 guys. You go swim in that 50-meter relay because they need 4 people for that. He doesn't care which lane they get into. He doesn't care about any of that. He just wants them to go swim. And so the order doesn't matter. This is called a combination. Now we're just trying to pick a group of objects. We're not worried about what order we pick them in. Notice that we still have no repetition. Combinations still have no repetition because you can't pick the same swimmer to swim in that same relay twice, right? They can swim in the relay once. So no repetition, but order does not matter. So when you're selecting R elements, R is the number you're choosing, N is the number you're choosing out of. There's no repetition. Number of combinations, so groups, not orders. It's going to be like this formula. It looks pretty similar. You have the same n factorial on the top, see the same n minus r factorial. The only difference is it has an extra r factorial on the bottom. Basically what this extra r factorial does is this guy right here will divide out the orders. So by making the bottom of the fraction a little bit bigger, you divide out all the possible different ways of rearranging the things. And so this will just give you the number of groups and not the number of arrangements. So that's why this is the formula we use, and we don't care about order. Okay, so how many ways could your swim team coach pick 4 swimmers out of your team of 10 if he doesn't worry about order? So order doesn't matter. And there's no repetition. You can't pick the same person twice because they can't compete with themselves. So then he would do, out of the 10, that's your n because it's the bigger number, 10, you're going to choose 4 of them. That's the bottom number. The R number is 4, so 10C4. And then we do 10 factorial on the top, bigger number on the top. We do the 4 factorial on the bottom times 10 minus 4 factorial. And that's formula. Now it's similar. We still do 10 minus 4 get 6. So we end up with 10 factorial over 4 factorial times 6 factorial. And then what we do is we cancel the 6 and the 10. So we get the 10 times 9 times 8 times 7. Stop with 6 because 6 is going to cancel. But we still have the 4 factorial on the bottom. So we get 4 times 3 times 2 times 1 on the bottom. So that's what the combination does to us. So instead of just being the top of just multiplying an answer, we have to take that and divide by the bottom. When you divide this, make sure you do the top, do the bottom, and then do the division last. Your calculator doesn't know about division bars, so make sure you type parentheses. You're going to type it all in your calculator at once. What you can do, it's definitely fine to type this all in there. As long as you have the parentheses, you can type in 10 times 9 times 8 times 7, close it, divide, do parentheses around the bottom, 4 times 3 times 2 times 1, and get that one. And you do get the answer that way. You got to make sure you put some parentheses. So the answer is 210. You'll notice that because now we don't care about the different ways you can order the group, the combination answer is a lot smaller than the permutation answer we got up here. Oh, I guess we didn't even do it. I forgot I didn't do that one. So this is a lot smaller. But yeah, if you just compare it with like the permutation answer we're getting millions. Here we're getting 200. So you can see there how much smaller it is. It's because we're not worried about the different ways you could arrange this. If I had just done the top, 10 times 9 times 8 times 7, that would just give us that would be the permutations formula. There's no dividing by the 4 factorial. We'd had 5,000 options for the swim meet if we'd done permutation. But since we're not worried about order, we're just worried about which groups of students can be chosen. That's why combination is much smaller. So combination, again, remember you do the factorial, 10 factorial on top, 10 minus 4 still on the bottom, but you also have the extra 4 factorial on the bottom where it divides out the order. So this 4, 3, 2, 1 is dividing out all the different ways you could arrange 4 people. Try one more combination. Go to Deadwood to play blackjack. Receive 2 cards from the dealer. How many possible hands could you receive from the dealer? So we're going to assume, standard 52 card deck. That means that the sample, the group we're picking out, N, is 52. We're choosing 2 of them. So we're only choosing 2. So we're doing 52, but we're choosing 2 of those. So we're doing 52, C2. we have 52 factorial on the top. On the bottom, we still have that 52 minus 2 factorial, but we also have that extra 2 factorial. Again, this is just getting rid of all the different ways to arrange it. We really don't care which order we get the 2 cards in our blackjack hand. You know, if I got 21, I got 21. Whether I got the, 10 and the 11 or the 11 and the 10, the order doesn't matter. So that's what we do. Don't worry about order. Order doesn't matter. And that's why we're using combinations. But what does matter is that there's no repetition, and you get 2 cards out of the 52 card deck. So that's why we use this formula. So we end up with 52 factorial over 2 factorial times 50 factorial. So everything 50 or less is going to get canceled. So we're going to have 52 and 51 on the top. At the bottom, we still have this 2 factorial, so we're going to have 2 times 1 on the bottom. So I would multiply that out. Again, I use parentheses on the top, so 52 times 51, close that, divide by 2 times 1. You can actually skip the times 1, because 2 times 1 is just 2. You could just put 2 on the bottom, that's fine. I just typed that as it was. And again, 1,326 possible hands. So that's why blackjack, there's so many different ways to play it, because, just one deal of the hand, you have 1,300 possible hands. And again, this is not accounting for order. So if I get a, ace of spades and a jack of clubs, or if I get a jack of clubs, ace of spades, those would count as the same hand, because we don't care about the difference of which order you got them. We just care about which 2 cards you got. That's how this works. Okay, so that's our counting techniques. The last page, I just want to talk real quick, talks about probability and coincidence, and just kind of illustrate a little bit why so many people have a hard time with probability, why so many people fall into misconceptions of probability. So let's talk about, probability and coincidence. So when 2 or more things happen together, we didn't expect to happen. I'm sitting in this spot, and lightning strikes that spot. I bought a lottery ticket, and it's a winning lottery ticket. Those are the 2 things. When that happens, we call it a coincidence. The probability of a specific coincidence occurring is very low. The probability that a similar coincidence might occur may be very high. For example, it's very unlikely I'm going to be struck by lightning this year. I really don't worry about it. I don't spend any time at all the whole year worrying if I get struck by lightning. The odds are 1 in a million. There's, that's pretty low odds. There's a lot of other things that are probably more likely to hurt me this year than getting struck by lightning. I'm probably more likely to get hit by a car than I am to be struck by lightning. So I'm just not that worried about it. But it is extremely likely someone in the U.S. will be struck by lightning this year. In fact, 20 people are killed and hundreds are injured by lightning strikes annually. So some people confuse these 2. They confuse the chances that they specifically get struck with lightning with the chances that someone gets struck with lightning. And yes, it is actually very likely that someone in the U.S. this year will get struck by lightning. In fact, lots of people will. There's probably hundreds. But my individual chances are very low. And those are very different things, even though they seem very similar. Because they're both thinking, okay, what are the chances to get struck by lightning? Well, lots of people get struck by lightning every year. But that doesn't mean I'm going to get struck by lightning, because my chances are really low. So for a certain lottery ticket competition, the chances of purchased ticket winning the jackpot is 5%. If all the students bought a ticket, what would be the chances that at least one student would win the jackpot? I wrote this for my in-person class. So I'm going to just say, let's say we have 20 students. So I'm teaching this to online students, and I don't know how many bigger classes this semester. I forget those little details. So let's say we have 20 students in the class. Because this is at least one situation, we're just going to do that. Probability of at least one would win. Remember, the probability of at least one winner is 1 minus the probability of losing times the number to the power of the number of trials. Well, in this case, if we had 20 students, that would be the power would be 20. Since there's a 5% chance of winning, there is a 95% chance of losing. So we would actually do 1 minus the 0.95, so 0.95, because that would be percent, the decimal form of that percent, to the 20th power. That would give us the chances that at least one of the 20 would win. So if 20 people all bought lottery tickets, and there was a 5%. This is a pretty high chance for lottery. That's way higher than real. This isn't going to be $1 million prize. This is probably $1,000 prize or something. Okay, 1 minus 0.95 power of 20. Okay, and that should tell us the chances. So in this case, there is a 64% chance that at least someone will win. So even though individual people have a 95% chance of losing, the chance that at least one person will win is better than 50% odds, and that's only 20 people. This is why, even though the lottery has terrible odds, and I will never buy a lottery ticket, I will not waste my money on a lottery ticket because I know I'm just basically might as well take that dollar and throw it in the garbage bin. I mean, the only reason to get the lottery instead of the garbage bin is like maybe I want to pay more taxes. If you like paying taxes, the lottery is a great way to pay taxes. But otherwise, there's just no point in doing it because your individual chances of winning a lottery are so low, they're just so minuscule, it's not worth wasting your time or money on it. But it's very likely at least one person will win. Even here we just have 20 people entering, and we already have 64% chances. And you think about the real lottery, and there's millions and millions of people playing every week. And out of those millions of people, of course, one person's going to win. But the chances that someone wins the lottery and that you win the lottery are astronomically different. Just like here, we went from a 5% chance of winning to 64% chance at least someone will win. What if we up the ante and say, okay, now students buy 10 tickets. So out of those 20 students, there's 10 tickets each, so we do 10 times 20. We actually bought 200 tickets, the students did. Now, what are the chances that at least one student will win? So again, we're doing the probability of at least one winner. Those 20 students with 10 tickets each. So we do 1 minus the probability of losing, which is 0.95 again. But now this time it's to the 200th power because we bought 200 tickets. So the students bought 200 tickets. We're going to do the 0.95. And now our power is 200. So even though each ticket they bought has a 95% chance of losing, most of those tickets are going to be loser. By the time they buy 200 tickets, they actually get up to a 99.996% chance that someone will win. So this is what I was talking about. The chances that someone will actually win the lottery are very high. There is very likely someone will win the lottery, but don't confuse that with the chances that you will win. And I think that's what happens a lot in our real life with probability. People, they confuse the two things. They say, oh, well, someone wins the lottery, it could be me. They don't realize that when you buy a ticket, your chances of winning, it's not just based on all those other people buying stuff. It's based on what the chances are. You count the number of options, for how many different ticket numbers you could pick, and the fact there's only one right number, one out of those 292 billion, it's astronomically small. You're not going to win. And I've never met someone in person, that I know that someone actually won the lottery. It happens. Because out of the millions of people playing, at least one person's going to win. But don't confuse that with the fact that you have good chances. And that's what people do. You think, oh, I'm going to be the lucky one. I'm going to be the one that wins. And it's not going to happen. I'm sorry, I hate to say it, but it's not how it works. It's a misunderstanding of probability. So hopefully this unit has helped you understand probability a bit better. Got a little bit better grasp of it. Hopefully at this point I've convinced you not to waste money on things like the lottery and casinos that are set up against you. Again, if you like to play a few games at casino and just hang out with friends or whatever, that's fine. There's nothing wrong with that. But if you go into a casino expecting to make money off the casino, you don't understand probability. The casino, they have mathematicians who are paid to make sure that doesn't happen. It's the same thing with pretty much every big corporate probability type game thing where they say, hey, you have a chance for this or a chance for that. They've set it up where, yeah, someone wins, but the majority of people, they just, don't get anything. That's how they set it up. So just be aware of that. Be ready for that. That's part of our world and our life is knowing that most of these games have chance. The big companies and the, casinos and lotteries, they are set up on purpose so that the players lose. And you have to understand that. All right. I'll let you go. We have the test coming up for that Unit 3 test. Make sure you're getting that scheduled and getting ready to do that. And I will see you next unit where we start math and units.